let's get down to it. Earlier this week, we started Fourier series, okay? And the idea was to continue the work that you've already done at school and at university on geometric series, Taylor series, Maclaurin series. Okay? So if you weren't here, that's fine. But this is an example of a Fourier series, and these things here, the A0, A and B, are called the Fourier coefficients. And I calculated one of them, and you basically get them from integration. But let's just remind ourselves, what can Fourier series do? Okay, what can Fourier series do? Okay, so I showed this in the lecture on Wednesday. Here is a curve that is periodic, and it's an odd function between -1 and +1. You just spin it around, right? Okay, so what can Fourier series do? Like any other series, the idea, at least in some part, is about approximation. Okay, so here is part of a Fourier series involving sine, and it's basically just a sine curve, right? And it's supposed to approximate the red and blue lines as best as is possible, right? But that's not a great representation. So what happens if we add another term to our series? We get a bit more of an approximation, and we can continue that up. So what Fourier series does, it uses cosine and sine, periodic functions, to approximate other periodic functions. And the nice thing about Fourier series is you get a nice tight representation over a large interval, right? Over basically the whole real line, which is something that Taylor polynomials, Taylor series, Maclaurin series can't do. Okay? All right, so we derived one of those Fourier coefficients. I said the other two follow out is a bit more involved. But in order to come up with this Fourier series, you need a few things. You need half the period, okay? So that's where the L's are. And you need these Fourier coefficients, the A0s, the ANs, and the BNs, right? And you do that through integration. Now, sometimes those integrals, so the integrals, let me just zoom out. These integrals here, here, and here simplify massively when the original function is odd or even. So I made some notes down the bottom on how you can work smarter, not harder. Okay? When you've got an odd function to start with, the Fourier coefficients massively simplify. Okay? Massively simplify. So you should use that bottom line as often as you can. Okay? That's the best advice, some of the best advice that I can give you. Okay? Now, we did an example. Here it is. Okay? So this is a bit like a square wave or a rectangular wave function, something like that. You've got a lot of switching on and off, and basically we've got this simple function f of t, and we're going to represent it through as a Fourier series which looks super, super complicated. Yes, good work. So, although I don't like headphones, food and drink is fine, right, if you want to bring them into lectures. I don't care what you law people say, right? Now, so let's just refresh our memory about what we did. So in this case, you can see the example that we start with has a period of 2 units, because you take this bit, you copy it, you move it, and you paste it. Copy, move, paste. Okay, so every 2 units, the graph repeats. So half of that, of course, is 1, so the L in this situation is 1. We also see that this part of the function is odd, so instead of using these things, this will be 0, this will be 0, and you multiply this by 2 and you integrate over half the interval, 0 to L. Okay? So we did that, and we had some fun and games with simplifying cosine n pi, right? So cos pi, cos 2 pi, cos 3 pi, cos 4 pi. And we got down to these many but equivalent representations. Okay? So, you know, this was this and that. That's sometimes 1 and sometimes -1. It actually follows this pattern, and then that'll either be 0 or 2, -2, sorry, and you get this, okay? So that's 0, you get this, plug it in, and then simplify. But the one representation to rule them all is the bottom line. Okay, you can write your series in many different equivalent forms, okay? But if you just write out some of the terms, you'll actually see what you've got. So I would also recommend this. I would also recommend it. Okay? All right. So there's your Fourier series. We're not sure what to do with it, but we are going to use it in solving partial differential equations, like the heat equation, the wave equation, Laplace's equation, a few other things. Okay? So, bless you. So the picture is the first 10 terms of your Fourier series added together, right? And so you can see it's a bit like a wire that gets wrapped around the black curve, the original black curve. And the nice thing about it is the wire really does a lot. It can bend itself so it can go and navigate the jumps, and it's still a nice, smooth, continuous, differentiable function. Okay? Now, down here, this, basically these things tell you about the value of the Fourier series at certain points. If you've got a nice continuous function to start with, then the Fourier series and the original function are the same. And if there's a jump, the value of the Fourier series at that point is the average of the two limits. Okay? And then I finished off with an exercise that didn't have an odd or even function. But can you remember what we did to this function to make it a nice function? What did we do to that curve? Who was there on Wednesday? John Pork was there.
We shifted it down. I think it was half the unit. Yeah. Mm-hmm.
Exactly. So that function's not odd or even. It's odd and even, right? But we can make it odd just by shifting the graph. Okay, so that's what I did. Okay, so we get another representation. Okay, so questions so far, people? Questions so far? Good question. Here's one at home. Is the Fourier transform very similar? I wouldn't say it's very similar. And it's not quite as accessible as this stuff because you've got to know complex analysis for the Fourier transform. But it's a good question. If you do want to see something about the Fourier transform, I do have videos about the Fourier transform on my YouTube channel. Okay, so just search for something like partial differential equations, Chris Tisdell or something. Yeah. Okay, so it's a bit weird because you start off with a really simple function and you get this monstrosity, but it's going to be useful, okay? It's going to be useful. Okay, so let's get into some new stuff. This one, this one and the next example, which I hope to get to. Yep. It's really got some classic Math 2019 questions in it, okay? So this is sort of super classic, as far as I'm concerned, Fourier series questions for this course. Yeah? They're really, really important. Okay? So In the motivation, we talk about odd or even functions, but this question goes a little bit further. Okay, this question goes a little bit further. We already sort of know that. We know that things simplify when you have odd or even functions. But let's read the question carefully. You've got the function between x equals 0 and x equals 1. It's the function is x. Extend f as an odd or even function with period 2 and sketch the graphs. Okay, so what does it mean when I extend a function? Does anybody know? What am I talking about? Extend as an odd or even function. Anyone know? Well, let me show you. Let me show you. Here, I'm only starting with the function defined for x between 0 and 1, right? But if you look at all the examples that I've shown you, the main starting bit is not between 0 and 1 or 0 and L or something. It's always between something like negative L to positive L, negative 1 to positive 1 in this case. Okay? So in this situation, we need to extend the domain of the function so that it's an odd function or an even function and it's got a period of 2. Okay? So that's the first thing that the question is asking us. Extend f as an odd, let's say an odd function, f sub o, with period 2, and sketch the graph on this interval. Okay? Extend f as an even function, f sub e, with period 2. Okay? So we just need to work out what's going on there, and I'll do the odd one, even one first. Okay, just give me a sec. Okay, let's extend as an odd function. All right, so in this case, I want to take that function and extend it to the interval negative 1 to positive 1. Okay? Negative 1 to positive 1. That's got a length of 2, and if I just repeat it, then I can do what I want. So if I'm doing this one, I'm going to start with this. Okay, and I want to extend it onto the interval negative 1 to 1, let's say. How can I make that an odd function?
You can define x between negative 1 to 0 as just negative whatever its value is from 0 to 1.
So what would it be?
Pretty much in this case, I think it would actually just be x.
Mm-hmm. Yep. Not a trick question. So if I just extend that line in the same direction, yeah. That's my building block. Okay, now it's not defined at x equals 0. Doesn't matter. Fourier series don't care because it involves integration. Okay? So now let's extend it with period 2. What can we do? What would a strategy be? Who can tell me? when we extend it as a periodic function, essentially what are we doing with the graph? I did it with the first example we talked about today. What are we doing? Huh? Yeah.
We copy paste it along the x-axis.
Yes. So you see what we've got? That's our basic building block. We copy everything, we shift it and paste it. We copy everything, we shift it and paste it. Okay? So let's take that bit. Take this bit, move it this way. Okay, so you just need to pay a little bit of attention to the open and closed dots, basically. Okay, so that's the odd case. I'll leave the even case alone for a little while. Okay, but let's just find it. They want us to find the Fourier series of the even and odd extensions of f, right? So let's call this f sub o, right? What are we going to get? Okay, well, that's odd. So let's have a look at our situation here. F's odd. So a sub naught and a sub n are all 0, and this is 2 times that integral. Okay? So in this case, L equals 1 because the period equals 2. So you halve that. Yeah? So for the Fourier series of this odd extension, these coefficients are all 0. Great. So I only have to calculate one set of coefficients. Yeah? Okay, so that's my doubled integral. So I'll put in L equals 1, and I should get the following. Now, what is f of x on the interval 0 to 1? Who can tell me? What is f of x on the interval? Actually, that should be like O there, right? What is our function on the interval of 0 to 1? It's just the x function, exactly, thank you. Sometimes you just have to look and go, okay, where am I? Where am I in the interval? Okay, so this will be x times sine n pi x on 1. And so we're integrating this. Can anyone suggest a strategy to integrate? By parts. It's a product, we can try it by parts, right? So if I was doing this by parts, I would go, okay, I'll let this be u, this be v dash, right? So ABP. So if u is x, the derivative's 1, and the integral, you'll get a negative cos, and you'll divide by the n pi. Okay? So now I just put those together into my integral and I'll get something. Yeah? Okay. Okay. So integrate by parts. Okay, so it's u times v minus the integral of the product of the two things that you just thought of. Right, so that's a negative. I want to have a negative there, so it'll be positive. Okay, so let me move that up a bit. All right. All right, so in the first part, what's going to happen when x equals 0? It's going to disappear, right? And so the only thing affecting the first part is when x equals 1. Okay? So when x equals 0, it disappears. And I know our old friend cos n pi, we can simplify that in some way. Let's do this integral. This is going to become sine, and I'm going to divide by the n pi as well. Okay? So, the second part looks a little bit difficult, but what happens when x equals 0 in here? 0. What happens when x equals 1? It's also 0. Okay? So this thing here actually doesn't contribute anything. Okay? Why? Because sine pi is 0, sine 2 pi is 0, 3 pi is 0, because it oscillates, right? Okay? So that's good. All right, so this is negative 1 to the n. There. Okay, so I'll just leave it like that. You can simplify that by taking out the negative, doing all that sort of stuff, but I'm not going to do that, okay? All right, so what is our Fourier series? Well, we know that's 0, we know that's 0. We've just calculated that through this. So now I can just write that. That's going to be 0, that's going to be 0. I'm going to get a sine series. Okay, so take Bn and replace it with that. I can take the negative 2 on pi to the front. Ta-da! Okay, and you can write out some terms of that if you want to. Okay. Questions? That one was a bit nasty because it involved integration by parts. Okay? So if you get something like that, just recognise it, navigate it. Okay? So what happens with this series? Let's actually write out a few terms. I said I wasn't going to do it, but let's just do it. Okay, so for n equals 1, I'm going to get negative 1 here, right? And then sine of pi x. Okay, so for n equals 2, I'm going to get 1, positive 1 there and a 2 down there. And then for n equals 3, I'm going to have another sign change. Okay, so you can see in that expansion, the coefficient of all the signs is oscillating from positive, negative, right? So if you're ever worried about your answer for these kind of problems, sometimes it's helpful just to write out a few terms in the series, okay? Then you can at least compare it with your friend or your mate or ChatGPT and just see, well, yeah, that's the same. You've written it like this, I've written it like that, but they're actually the same thing. Questions? Questions?
In the third line from the bottom, how come you've rewritten cos n pi as -1 to the power of n? Could you just explain that?
Yeah, sometimes it's just easier to write it with a sort of a power or an exponent, right? Because you know, oh, it's -1 or +1, -1, +1, right? So if you draw a graph of cosine, so are you asking why is this and this the same? Yeah, so let's draw a graph of cos. It's a good question. Okay. What do you notice? What's the value of that green curve at x equals 1? Yep, and at x equals 2? Yeah, between -1 and +1. Okay. Yeah. Yeah, so n's an integer here, but here it's not. But that just tells you that cos of n pi for n an integer is either -1 or +1, and there's a pattern. Yep. Okay. No worries. All right. So there's a second part of this question, though. Okay. There's a second part of this question. Can you see this thing here? Show that, oh hang on, sorry, everyone at home can't see that. Show that this infinite sum of constants equals that. Okay? So this is a little bit more difficult, but you use the first part of the question to solve the second part. So the Fourier series helps us. That's the idea. Okay? All right. Okay, so we haven't done this bit yet. We've got that one. We haven't got that one yet. So if you go through and do that, how would you extend your function? It would sort of be like that, right? So to be like that, okay? Yep. And so that's how you would extend it as an even function, okay? So I won't do all the things for the SFE, but I'll use it to solve. I think I'll use it. Oh no, I'll use the first one to do that. This is the expansion for the even extension, right? Oh, sorry. Get that right. 1/2 plus okay. All right, so that's the one way to write it. You might have seen in the previous lecture, I wrote this in an equivalent way using just odd values of n, okay? So you can do this using that. So let me show you that, and then I'll show you a third way. Because when n's even, what happens to this square bracket? Who can tell me? When n's an even integer, what happens? It just disappears, exactly. So when n's odd, we'll get -2 here. And you multiply that by the 4, you get -4. So okay, now if you don't like summing over the odd integers in this summation sign, that's okay. I did show you a third way to do this. Basically, you replace n with 2k minus 1. Okay, now, why is that important? Well, it gives you another way to express it, but it's particularly important, that form, for this problem here. Okay, so let me just zoom out for a sec. Yeah. All right, so here I'm going to put a question to the class now. How can I use that boxed expression at the bottom of the solution to solve the question at the top of the page? What can I do? What can I do? Any ideas? Try to find a connection between that mess down the bottom and that simple thing up the top. Any ideas? Nope. Oh, false start. I'll give you a clue. Everyone at home, I'm going to check in a minute on what you're doing. But what happens if I have a magical thing and I cover that up? Does that kind of look like the thing up the top a little bit? Oh, yeah. So if I cover that up, the remaining expression and the thing up the top are almost the same, right? In fact, they are the same. So what will force cosine of this to be 1? Yeah, x equals 0. So I say, okay, I'm going to substitute in x equals 0 here. That's going to disappear to 1, and then I'm actually going to get this expression, something like this. Okay, so let's unpack that a bit more. Yeah. How can I do this? That'll do. So let's go with the even extension Fourier series at x equals 0. Okay, so we can simplify that sum by taking the negative sign out. Oh my God. Okay, so I've kind of got what I was hoping for there, but I want to set this equal to something because I want to, show that it's pi squared on 8. So how can I do that? Well, do we know the value of this at x equals 0? It's 0, right? Why? the Fourier's theorem says, as we approach this side and this side, the average of the two limits of the original function equals the value of the Fourier series approximation. Okay? So I'm going back to my original graph. I'm taking limits from both sides as x approaches 0, and I'm saying, what's the average of the two limits? Well, you've got 0 on one side, 0 on the other side. The average has got to be 0. Okay? So this thing's 0, this thing's also this mess. We combine. So we move it around. Bring that to the other side, multiply. Wow. Wow. Okay, so those annoying series that you saw in first year, you can use Fourier series to do a lot with them. Okay. So a good question here is, how did I know where to put, like to put in x equals 0 there? Well, I wanted something that would simplify as much as possible. So I wanted to get that to 1. If that was 1, then things would work out nicely. So my objective was to make that 1 somehow, and x equals 0 will make it 1. Questions? What's happening at home? Yeah. Yeah, Frank, exactly right. You too, Zach. Yeah, good on you, Daniel. So the graph extension, yeah, so let me put this up on the... So for the even extension, the graph looks like a sawtooth wave, I guess, or a zigzag. A zigzag's a better way of expressing it. Okay, so you need to be able to do that. Otherwise, you're not sure what your Fourier series is going to look like. Questions, comments, observations, criticisms, commentaries, critiques.
Geometrically, like, where's the pi squared on 8 coming from? Like, is it the area under something?
Geometrically, no, I don't think so. I mean, basically, yeah, I don't think it's coming. I don't think it's coming from anywhere. It's just this function. This function at x equals 0 has to equal 0, doesn't it? No, it has to... Yeah. So this crazy representation at x equals 0 has to be 0. And in order to get that to work, you know, obviously that'll be 1. You're left with a sum of something, and that's got to give you your pi squared on 8. Otherwise it wouldn't work. But geometrically, I'm not sure. Well, we're trying to think about it from Fourier series perspective. So I guess my point with these ones is special cases of Fourier series can be helpful. I guess that's what I'm trying to get across. Yeah. There's probably some first year techniques for proving that, but not using Fourier series. Questions at home? Questions here? Okay. Oh, yes, there's a question.
It'll probably make the whole thing more complicated, but you said that we used 0 because it was easy to simplify the whole thing since everything goes to 0 at 0. But since we have a period of 2, would we also get the same thing if we took x equals 2?
Well, let's go up to our... So we're thinking about the blue curve now, right?
Yeah.
Yeah, you would. You should.
Okay, so if we substituted 2 there instead, it would still be the same.
Should.
Okay.
I can't see this. Unless there's something I'm missing, right? I mean, I would choose the simplest point possible, right? But unless there's something I'm missing, you should... I mean, the function, it goes to the same value, the limits, so it should be the same. Right? Okay. So that is odd and even functions, which are amazing, right? So let me show you one more. Okay. I think we can do... I'll throw this up in a minute, but let's see if we can answer the questions without actually doing any work. Sounds pretty good, doesn't it? It sounds too good to be true. Okay, whoever this guy is, Juan Carlos Ponce Campuzano, you're teaching this class now. I'm no longer teaching it. Right? Okay, so the question is down the bottom, right? It's 3 and then -3. Okay? So is this an... let me put this up for everyone at home. Is this piecewise defined function odd or even? It's odd, exactly, right? It's odd. So we know we're going to get a bit of simplification. But let's just draw the function, and then we can have a look at the Fourier series, what the graph of the Fourier series should look like, right? Okay, so it's 3 on that interval. It's -3 on that interval. Okay, and we copy and paste it. Oh, and it's open and open. Copy, paste. Okay, so let's see if we can actually work out these values. I've got them there, written there, but from the graph. That's the graph of the original function. Okay? So based on the third and the fourth dot point up the top, what would you expect the value of the Fourier series for f to be at x equals 0? So what is this? I've got it down as 0, but why? Why is it 0?
When we convert the function into its Fourier form, it'll connect all the points together. And so we take the averages, as you said earlier, between the 2 points that we're connecting.
Mm-hmm. Yep, perfect. So if I'm looking at this graph closely, and I want to find out what the value of the Fourier series is there at that point, f's not defined there, right? So the limit going this way is +3, the limit going this way is -3. The average is 0. What about at x equals 1/2? What should the value of the Fourier series be at 1/2 and why? I've got it at +3. Why is it +3?
I'm not sure if it's a trick question, in the sense that it's like between 0 and 1, so it's just 3.
Yep. So basically the original curve, the original function is continuous at x equals a half. There's no jumps. So, you know, the limit exists and it's the value, right? So, you know, these two things are equal at nice points. Okay? All right, so what is the actual expansion? There it is. Okay? There it is. So the idea with the limits and averaging the limits is called Fourier's theorem. Okay? Fourier's theorem. We're going to see a lot of Fourier, especially in the heat equation for partial differential equations. Okay? So in the bottom two lines, I've just solved the thing and I've written out the Fourier series. Note that it's also odd, so there's two things that are zero, which is nice. Okay? All right. So I don't like putting things up and dumping them, but odd, exactly, Zach. You're on fire. All right, questions? Comments? Critiques? Complaints? All right, let's take a 10-minute break. Revision? Yeah, we'll do revision for lab test 2 after the break. Stay tuned, everybody. All right, here we go. Now, I've done quite a few of these questions already in lectures, and I thought I'd like to start, with your permission, of course, with the matrices part, okay? And then we can work our way backwards if you want, all right? So let me just grab my notes here and see what we have. All right, now there's a lot of repetition here. All right, so let's start with a relatively easy one. Now, these kind of questions are just variations on a theme, okay? They're quadratic surfaces, quadratic forms. It's basically a generalization of completing the square, okay? And what you're asked to do is you start off with this quadratic form, all right? It's like a polynomial with order 2, and you want to find a matrix which will be a symmetric matrix such that x transpose times that matrix times x equals 448. So you can see the right-hand side is the same, yeah? So it's basically taking the coefficients here and putting them into a matrix, okay? Okay, so down the main diagonal, what goes down the main diagonal for these matrices? Oh, I've forgotten. It's been too hot today, and I've been sweating and whatever.
The coefficients of the squared terms?
Mm-hmm. So down the main diagonal, we would write the coefficients of x squared, y squared, and z squared. So over here, 16, 23, und 10. Oh no, not like that. You go in there. Okay, now what about this other diagonal? What goes there? Yeah, half of the coefficient of x, y. Okay, so this would be -6. Und this would be -6. All right, what about the other diagonal, the 3 and the 7? That will be half of... What's it going to be? Yeah, xz, so that'll be 0 and 0. Is that right? Sort of missing a term. And then the 6 and the 8, it should be half of that, right? So 6 and 6. Does that look right to everyone? Okay, so I won't press how did I do because I want to put all the information in first. All right. So you are given that the matrix A has eigenvalues 4, 7 and 28. Hence, the equation of the surface in terms of its principal axes, capital X, capital Y, capital Z, can be written as this. Okay, so what I've taught you in lectures, how many negative signs are in this simplified expression? None. So is it an ellipse, a hyperbola, one sheet, or a hyperbola, two sheet? Ellipsoid, yeah, ellipsoid is better. Yep. So if I scroll down, so I'll leave that for a minute. Does that graph look right? What's that? What kind of graph is that? Yeah, it's a two-sheet hyperboloid. It's a one-sheet hyperboloid. The third surface was just right. Right? That's the ellipsoid. Okay, so how do I come up with this number 4? The shortest distance from the surface to the origin.
So in this case, we would make it the square root of the answer over the largest positive number, in this case, which is 28.
Yeah, so you know that the closest point, if we go back to our picture, right, we go back here for our ellipsoid, that the closest point to the origin, which is somewhere in there, lies on one of the axes, either the capital X axis, the capital Y axis, or the capital Z axis. We've just got to work out which one. So I'm going to set 2 of these things to 0, and like you say, that's the largest number out of 7, 14 and 28. So I'm going to set those 2 to 0, and then I'm going to divide by 28, and I'm going to take the square root. Okay? So 448 divided by 28, square root gives you plus or minus 4. The distance, therefore, has got to be 4 units. Okay? So, shall we use the one shot? How did I do? Yes! Oh, it's all green. Okay? Questions? Yeah, if there's no negative signs, and that's positive, then it's got to be an ellipsoid, right? If there's one negative sign, it's an hyperboloid with one sheet. Okay, one sheet looks like this. Okay? And if there's one positive sign and 2 negative signs, it's a 2-sheet hyperbola like that. That's the way I remember it. Okay? Maybe not very scientific, but that's the way I do it. Catch up. All right. Here's another one. Okay, now people were freaking out over this. People were freaking out last week. They were contacting me in the lectures. They were contacting me today. They go, Chris, this is broken. This is negative. This is negative. This is negative. Doesn't matter. They can be positive or negative. But there is a problem if you get down here, and that's negative. Because you've got negative, negative, negative equals a positive. Quick maths. Okay? So this is the same sort of deal. You can see I filled this one out earlier. And this main diagonal with x squared, y squared, z squared, etc. Yes, boss. Oh. Oh, fast trick. Let me have a look. Is it the same style as this? Okay. All right. So, yeah, I can do that. So, the main diagonal is the coefficients of the squareds, and then the other diagonal bits are half of the other coefficients. All right. So, two-sheet hyperbola, because there's two negative signs. So how can I find the distance based on that simplified expression? What do I actually do? Can I put big X equals 0 and then like move things around? No. Okay? The only thing that makes sense is to set these two things to 0. Okay? Otherwise you get a negative equals a positive, which doesn't work. Okay? So you would set big Y and big Z to 0, you would divide by 121, and then you would take the positive square root. Okay? All right, so this will be a two-sheet hyperbola because it's two negative signs. So not that one, but the third one was just right. Okay? We're getting the hang of this? Same sort of deal. Oh, 20, 28? Okay. This one? Next one? Okay. Okay. So, the matrix, you're told, has an eigenvalue of 2. Now, it might be repeated, it might not be, right? It doesn't look like it's repeated by my answer. Find an eigenvector corresponding to lambda equals 2 in the box below. Okay, so here we go. Here's one I've created earlier. Okay, so for this one, I just reminded everybody here that if lambda equals 2, if that's an eigenvalue, then 2 has to satisfy this equation, right? So we know that that's true, and then we solve this system of equations. Okay? So if this is my m minus 2I is going to be, well, -1 minus 2 down the main diagonal, minus 3, sorry. 1 minus 2, I'll give you -1, and 2 minus 2 is just 0. And the rest of the thing stays the same. Okay? So you've basically got 3 equations and 3 unknowns, V1, V2, V3. Okay? What does row 1 tell you? Come on, you've got to help me out here. What does the row 1 tell you? V1, 0. And what does row 3 tell you? Huh? So row 3, what does that tell you? No. It's a bit of a trick question. Okay? So let's look at the first row. Negative 3v1 plus 0 equals 0. Negative 6v1 plus 0 equals 0. So row 1 and row 3 give you the same information. Okay? It doesn't tell you anything new. Okay, but row 2, what does row 2 tell you? Row 2, 6v1 minus 1v2 minus 1v3 equals 0. Now, v1 0. So this is going to disappear, and basically I've got v2 equals negative v3, or v3 equals negative v2. So I just choose values. This is already fixed, but these two things are not fixed. So I've let v2 equal 1, so v3's got to equal the negative of that. Okay?
Sorry, I'm just asking if we switch that around, will it still be accepted for like 0, negative 1, 1? Beautiful.
Shall we test it? Let's test it. Remember, people get angry sometimes because there's too many choices. You know, it's like when you go to a restaurant and the menu's like 20 pages, and it's like, oh, there's so many choices. I can't make up their mind, right? So do you know this psychological theory? Like there's too much choice. Okay, does anybody know what you're supposed to do? You go to a restaurant and there's like a 30-page menu, right? What do? It's the same with eigenvectors. Okay, I'm going to make a connection here. I hope you're not too hungry.
Not too sure, but I've heard that you do basically categorize everything into 2 choices, and out of the 2 you make the choice of 1, and then again you have another two until you take like the very last one.
Oh, so it's like a divide and like you're splitting, and then okay, all right, that's interesting. I haven't heard that. Anybody else? Anyone else want to play? Just randomly pick one. That might work.
Not sure if I'm mistaken, but like the eigenvectors, like technically there's a lambda thing out at the front. So like any what do you call it? Scalar multiple works. So that's why if you multiply by negative 1, you get 0 minus 1, 1. It still works.
Yep. What about the food though? Okay, so here's the theory that I'm familiar with, right? You get a 30-page menu and you don't know what to order, right? Maybe you're visiting a foreign country, you don't know the language, whatever, you know. The psychologists say you should find one thing, the first thing that you like, and order it and close the menu. Okay? Just find one thing, that's it. Right? Forget about FOMO and the fear of missing out. You're supposed to just find the first thing you like and order it. Okay? I reckon it's the same with these things. As soon as I say, let v2 equal 1, v3's got to be the negative of that, right? But I could have mixed that up and said, okay, I'm going to let v3 equal negative 1, and then v2 will be, v3 equals negative 1, so that'll be, positive 1, and then v2 equals negative 1. Let's see if we can move it around and see if it still works. Okay, so in my, hang on, if I choose how did I do now, I won't, will you agree that that's correct? Okay, let's move it around. Oi. Okay, so we tested it. Still correct. Okay, so what happens if we went a bit crazy? Let's see what happens. Does that look about right? Hey. Still works. Okay? I dare you to put that in your lab test too. Any questions at home? Yeah, just ask ChatGPT to choose something on the menu. That's not a bad idea. Yeah, you can row reduce if you want to with these problems. You could ask, well, I guess you could probably ask the waiter or the waitress, but if you don't speak the language, it'll be hard, right? I remember I lived in China for a while early in my career, and I remember taking out some professors, right, to a local restaurant, and you know, thank God they had pictures of the food, right? But yeah, it was pretty clumsy, and you can't. I couldn't just say, "Oh, what's good?" You know, I'm trying to impress these people. What's good? But anyway, we survived. We survived. Other questions about this one? All right, so that's our eigenvector. Was there another one? Huh? 27. If people have requests at home, please let me know. Whoa! This is the one with the repeated eigenvalues. Right? Is this it? Or not? Okay. Quick way. Well, you only have to calculate one thing, right? So if I was doing this one, the eigenvector for that is that vector, right? So you don't need to calculate that. Yeah? And then we have a repeated eigenvalues. So that's good too. Okay? So how did I do that one? How did I do that one? Okay? So there's only one set of equations to consider, and they're all the same except for one row. Okay? So I started with this because I wanted to get, you know, this is going to be the first row of my matrix, and then I want to get a column, sorry. I want to get two other columns. Okay, so I want to get, you know, these vectors from here. Okay? So I've got a system of equations. I can row reduce. And then I look for the non-leading columns. The non-leading columns. So that's one non-leading column. That's another leading column. So this is the sort of the V1 column, the V2 column, V3 column. So I'm going to let the non-leading columns be my parameters. Okay? So this row gives you this relationship here. Is it quick? I don't know. Sometimes I think it's quick and students go, "Can't you make it quicker?" I'm like, I can try. I can try. Okay, how did you do it? Did you do it already or not? No. Yeah. Okay. Questions? So if I'm going back to my, you know, this is going to be your V2 vector. This is going to be your V3 vector, right? Yep. So if I go back to what answer I should be putting in, it's those columns there. So that column goes there. that column goes there, that column goes there. Okay. I don't think it's a bad question. I think you can do it. Right? You just need to know what to do. Oh yeah. Suddenly, this got a lot more interesting. Frank talks about the 37% method. You go through the first 37% of your choices, you pick out the best one, then you go with the next option. Okay. Do people watch movies here, like Netflix or Amazon Prime or something? Anyone into it? Right? How long do you give a movie before you realise you're not enjoying it? Do you watch the whole thing? 5 minutes? What do you reckon? But let's say someone, a friend's recommended a movie to you. How long do you hang on before you're like, nah, this is terrible? Okay, all right. What? Yeah, it's a hot take, yeah.
But like, it can be the wrong time, right? Like, you could be watching a movie, you could be 5 minutes in, but it might just not be the day. But you can come back to a movie like a month, maybe a year later, and then it clicks for you.
Yeah. I'm like that with, I give it 30 minutes, and if I have to look at the clock or my watch or whatever, in that 30 minutes, I'm like, nah, I'm not enjoying this movie, because I'm distracted, right? I'm like that with music as well. Sometimes I have to prepare myself to listen to music for the same reason. It's like, oh, I don't know if I can handle that, or I don't know if I'm ready for that. Yeah. Good job, Frank. There's also a rule about interviewing people, right? How many people should you interview before you make a job offer, right? That's also a famous problem, combinatorics, probability. It's called the secretary problem, right? All right. Aha. All right, this is a good one. This is a good one, people. All right, now let's make things faster. Yeah? Let's make things faster. Find all of the eigenvalues of this matrix. Enter your answers in numerical order, from the smallest eigenvalue to the largest eigenvalue. Okay, there is a quick way of doing this problem and a slow way, and probably some other ways in between. Can anyone suggest a quick way of solving this problem? What might be a strategy? Any ideas? Any ideas? What do we notice up front? Oh, there's a couple of zeros in that second row. Can we exploit them somehow? Can we exploit them? The answer may surprise you.
So, as said, exploit as many zeros as possible. If I were to do this, I'd probably get even more zeros by doing some row reductions. Yeah. So you got the top row and the bottom row is very nice. You can get rid of the tens. And if once you have like a decent amount of zeros, you can just go do the determinant thing, and then your solution will be much easier to solve.
Exactly. So the idea is, starting with your matrix, you can modify it to make things simpler. I think that's what you're saying, right? So this is one of the ways that I've done it. Let me just see if I can find my working here. Yeah. So here's what I've done. Now this is one way. You don't have to do it this way, but this is for everyone at home. All right? Believe it or not, think back to Math 131 when we're doing matrices, right? You can expand a determinant along the middle row. The middle row. So you can. So the way I usually show you determinants is, you start up here and you work your way there. You do the cover up. But actually, what if I told you could start here and go that way? Right? No row operations required. Just expand it along that way. The only trick here, insteed of the determinants going positive, negative, positive, it goes negative, positive, negative. Now, if you want to change row 2 with row 1 and get the zeros up the top and do it old school way, you still need to put a negative sign because you're changing rows. You're changing one pair of rows. Okay? So I've gone, right, I'm too lazy to do any row operations. I'm just going to start there and go that way. And I would go, okay, it's zeros in that row and that column. So I multiply by the determinant of what's left and I add a negative sign. Then, it's 0 anyway, so who cares? Then I move on to that one. I cover that row, cover that column, and I multiply by the determinant of what's left. And who cares about that 0? It's in that row and that column. Well, sorry, it's in that row and that column. It's not going to change because it's 0. There. That's it. It's in its glorious, glorious form. You don't have to write that down, but it's just there to sort of say, hey, I'm tough. I can expand along any row that I want. Okay? Now, it looks like you're going to get a cubic equation, and you do, but it's a nice one. So even if you don't use these life-changing techniques, you still should probably, hopefully, be able to simplify. Okay? Now, I haven't seen a question yet where the eigenvalues are not whole numbers. So even if you get desperate, you can still use the factor theorem, K-calc, where you're plugging in numbers.
I guess another piece of advice that you did talk about before was if you get something where you can simplify it, but you only have like 2 of the factors figured out, and then you couldn't find the last one, you can just use the trace method to find the last one.
Exactly. Yeah, that's really good too. So let's talk about that. So you know that the sum should give you the values of, should be equal to, so the trace, the sum of the diagonals should equal the sum of the eigenvalues. So why don't we do a question like that? So that's an excellent check. That's really good. Yeah. So, -5 plus 2 plus 10 should equal the sum of the 3 eigenvalues. And if you know 2 of them, you can use that equation to get the 3rd eigenvalue. All right, speaking of this, let's have a look. Okay, so I think this is the way they want you to do it. You've got a dirty big matrix there with big entries, and you're saying, you've got 3 distinct eigenvalues, which is fine. So let me see if I can find this on the, no. Aha! No. No? Yeah. Okay, so people in the lecture theatre can see the computer screen. People at home can't yet. All right, so you've got a symmetric matrix, which is nice. It's got 3 distinct eigenvalues. You're told that. You're given 2 of the eigenvalues. 2 of the eigenvalues. So enter the value of k. Well, the trace equals the sum of the eigenvalues, so you want that third eigenvalue, just move things around. Now, I did do this using Desmos, right? I couldn't do that in my head. It was painful, I got to say. It was a bit painful. But I got the right answer in the end. Okay? And then, in part B, they're saying you're given that the symmetric matrix A has 3 linearly independent eigenvectors, which it should, right? Because it's symmetric, and symmetric matrices are nice. Here are the 3 eigenvectors, v1, v2, v3. Okay. Find an orthogonal matrix. So for this one, it's super easy. You're basically writing those 3 eigenvectors as columns in this new matrix Q, and you're normalizing each of the eigenvectors. Okay. Now they all have the same length. It's handy. That's convenient, right? So you only have to calculate one thing. Okay. Again, whole numbers, which is nice. So if I go and have a look at my answer, you can. Somebody mentioned, I asked this in lectures, can you put the 1 on 23 out the front? And someone said, yes, you can. So I tried it and it works. Okay, so shall we go for green? Right, let's go for green. Yes, and yes. Questions? It's good when you get the green going, right? Makes you feel good. Okay, so they're pretty much all of the matrix questions. Let's see if I've missed any of note. Yes, so you can see they repeat, right? Oh, did that one. Okay, now we're on to ODEs. Okay. All right, so I'm going to have a little show of hands, both here and at home, please. Just write a comment, smash that chat button. All right, there's 3 sections in lab test 2. There's double integrals. There's ODE, differential equations, and there's matrices. Okay? Which is the hardest section, in your opinion? Which is the hardest section? Which is the easiest section? Or are they all the same?
ODE and then what's the matrix, and then what was the other one? Double integration.
So ODE is hardest, or okay, and matrix is easiest. What do other people think? Is there a harder section, an easier section? Are they all the same? Are they like your children? You've got to say you love them equally, you know. Because they're all quite different. They're all quite different sections. You could teach them independently of each other.
Double integrals arguably could be slightly harder.
Why?
I don't know. Just can be. I mean, the ODEs are really straightforward. you can just sub in without even doing anything, we're just looking at the numbers. Same with matrices, but like ODEs, you have to like kind of calculate, you can make mistakes. That's why like it slightly could be.
I think also with double integrals, you really need to draw pictures. And people, I think, they find it difficult sometimes to relate a graph or produce a graph with some sort of two-dimensional region, okay? All right. Is there anything else you want me to cover? Let me have a look at what people have been writing at home. Is there anything else you want me to cover? Any other questions before lab test 2? Oh, okay, here we go. The polar stuff, I get lost integrating. Yeah, it does. You know, it's another set of coordinates, right? It's another set of coordinates. So instead of, you know, horizontal and vertical, you've got angle and length. Yeah.
So I looked at your video on like deriving where the R comes from in the polar, but I still don't understand where the R comes from.
Yeah, so basically so you're talking about the r d theta, right? Yeah. So I guess that's associated with a polar rectangle, right? So you watched that video where I derived it? Yeah. I'm not going to derive it now, but yeah, you'll find, like, okay, you can think of R is almost a bit like a scale. I didn't mention this in the video, but R is almost like a scaling constant. When you go between, say, rectangular coordinates and polar coordinates, R sort of gives you a scale factor of how you're transferring area and size. So that's another way to look at it if you want something more physical. But yeah, let me. They're sort of the two explanations I know. And you can think of area of a polar curve as like the sector of a circle, basically, right? So, you know, you basically chop out a wedge and then you cut a bit off. So you're left with the polar rectangle. But let me think about it, okay?
Can we just run through the question you have on the board there?
Ooh, yeah. Okay, people, the polar stuff, messed up ODEs the most often. I know, it's easy to make a mistake. I get it. So what did we have? This one. Yeah, all right, so do I have it? Yeah. Luckily, I've prepared some of these, right? So what are they asking you to do? You've got a DE, and they told you the two solutions to the homogeneous case, y1, y2, and then you're given this formula. And you're told about the Wronskian, which is the determinant, the bottom bit, and the right-hand side, and you've got to come up with these things. Okay, so hang on, I'll zoom right out. Okay, so I've got to calculate I1, I2, and they give us the formulas for that. Okay, so it's just a matter of simplifying, like plugging things in and then simplifying the integral as much as possible. Hopefully the Wronskian cancels out with something else, and it does in these examples. So e to the 6x. So that's pretty good. So e to the 6x will cancel, and you're integrating by parts. Okay, and I think that's what I've done. So you integrate here, you get something like that. You get something like that. Okay. So probably the one that I haven't discussed in class very much is the third one. What does w of x represent? Well, it's the Wronskian. Okay, it's basically a determinant. Okay. So let me see if I've got the answer to that. No, I don't have the answer. But anyway, that's how I did it. So those questions, they're not difficult, but there's a lot of words and a lot of equations and a lot of information, right? So, you know, sometimes I try to think, what would I do if English was my second or third language, right? Would I be reading all that? I don't know. Could I read all that? Probably not. Okay. Okay. All right, let's wrap things up. If people have questions, come on down. Get 100 next week, people. I believe in you. You can do it, right? You can do it. If you didn't do well in lab test 1, now is your time to even things out. You can do it. I believe in you. And I'll see you next Tuesday.